Okay, so you're going to try and do this expressing as a rational number. Now, a rational number is a ratio of two integers. So this should be a single fraction ratio of two integers. I did say you didn't have to kind of simplify it in its simplest form, so that's absolutely fine. So the first step is obviously to write x equals to... Now there's various ways. You can multiply x by 10, 100,000, but the trick is whatever you times it by, you have to line up the recurring digits. My rule of thumb is if there's one recurring digit, you only need to times it by 10. So that's 10x here, and that's 51.77 recurring. And then just write down the x again below it and line up. Now once you've done that, you're going to do a subtraction, and that's 9x is equal to, well, this cancels, this is 0.6. 51 subtract 5 is 46. That looks pretty good. And now x is 46.6 over 9. But remember, it's a rational number, so it's a ratio of two integers. So it's 466 over 90. Yeah, yes, it simplifies, but I'm going to leave it at that. Now over here, let x equal 3.412626. Now there's two recurring digits, so times by 100. So it's a simple rule. There are other ways of doing this for sure, which you know. I'm trying to choose the simplest way. So that's 341.2626 ... Then write down x, which is 3.4126 ... And then off you go. You can just do the subtraction again. This is 99x. You're going to get 6622. 6 subtract 1 is 5. 0. 12 subtract 4 is 8. 340 subtract 3 is 337. So x is 337.85 over 99, which when you kind of times both top and bottom by 100, is that okay? So that's a technique. It's just saying that in the world of number, that any recurring decimal is a rational number, can be written as a ratio of two integers, and pi is irrational. People investigated that for quite a few years now, and they've checked billions of decimal places that no part of it recurs. If someone found on the 10 billionth digit that kind of kept recurring, then we could really write pi as a ratio of two integers, but we can't. In fact, pi has been proven to be irrational, not rational. You might want to have a look at that. So I'll just continue with this page. It'll be a two-part video. Now, you should be able to unpack this. S is a set, and it contains elements x such that the x values are greater than -7 but less than or equal to 5, and x is an element of the integer family. So for sure you can list all of these. Okay. Notice we use those kind of curly brackets, parentheses for sets. But look, n of s is how many are there in the set, and there's 12. Okay. P is a subset, so a subset is any grouping of elements in the bigger set. So I could take 0 elements from set S, and that would be a subset. I could take all elements, and that would be a subset. Okay, so that's kind of what we want here. So a subset is a group of any elements taken from the original. So P is a subset of S, and P contains prime numbers. So list, look, P is equal to only the prime numbers, and look, 2 is a prime number. 1 is not a prime number. A prime number has only 2 factors, and exactly 2 factors. 1 has only 1 factor. Okay, so 2, 3, 5. And now let's have a little look here. So we're going to base all our work on 2, 3, 5. Okay, so 2, 3, 5. I'm going to set you a little investigation here. How many possible subsets? Okay, so here we're going to list all the subsets. The first subset is the null set. This is the set that contains no elements. Weird, but there you go. Now all the sets containing 1 element. So this is just a listing. All the sets containing 2 elements. Interesting, order doesn't matter. It's just a set, a group of numbers together. And there is one more set, all the sets containing 3 elements. Now look at the pattern here, 1, 3, 3, 1. 3, 6, 7, 8 in total. Now where have you seen that pattern before? 1, 3, 3, 1. Does that look familiar? Yes. Now look, watch this notation, because all of these are less than or equal to P, and P is 2, 3, 5. Now look at that notation carefully. This notation, the actual translation of it, let's get a pink on, is a subset. So this particular notation means it has to be containing elements which are in the parent, so let's call this the parent set if you like, or the universal set. All of these guys have to contain elements that are in P. It can contain 0 elements, but it can contain all 3. So this symbol is kind of like a less than or equal to, and this is the language to go with it, is a subset. Okay. Now I'm going to adjust this a little bit, because if we had this notation, this is a proper subset. And now with this notation, we've got the 2, 3, 5 here. But now all of a sudden, from the group over here, let me see if I can lasso it. From this group here, I can copy, and I can hopefully paste. Yeah, so look, it's only these guys that I can have now, because to be a, let's put the pen back on, to be a proper subset, you can't actually be the same size as the parent set or the universal set. So this is how to use those 2 symbols correctly. This one here is a proper subset, and this one here is just a subset. Okay, so just have a little think about the distinction between the 2. Alright, so here's your mini investigation, and it is a mini investigation, but what happens if we have U a universal set, okay, and the number of elements in U is equal to 5 or 6 or 7?